The main thing that group theorists like to do is they like to compare and contrast groups. So that's what we're going to do here. We're going to compare, well, and contrast U55 and U75. U55 in terms of elements is all the positive integers less than 55 that are relatively prime to 55. So for example, 55 is 5 times 11. You want to avoid multiples of 5 and multiples of 11. Things like 4 would be in there, things like 7 would be in there, etc. 75 is what? 5 squared times 3. Avoid multiples of 5, avoid multiples of 3. First off, you might wonder, do they have the same number of elements? You might also try to figure out, are they isomorphic or not? As far as figuring out whether they have the same number of elements, you can certainly try to list out all the elements, but it's more efficient to use the facts in chapter 8. For example, use the prime factorization, 55 is 5 times 11, to say that U55 is isomorphic to the external direct product of U5 and U11. That's a fact in chapter 11 that you can do that because 5 and 11 are relatively prime, is the reason that works. Okay, if you look at the corollary on page 177, that's the reason that works. If you look further down on page 177, right here, so this part, it's not labeled as a theorem, but you could effectively think of this as a theorem. Maybe you want to circle it in your book, labeled as a theorem in your book. Some facts about U groups there, where the thing inside the parentheses is a power of a prime. U2 is actually a trivial group, one element group. It's isomorphic to 0 as an additive group. Technically speaking, its one element is the number 1 as a multiplicative group under multiplication mod 2. U4's got 2 elements, U to the 2n. U of 2 to the n power is isomorphic to this, which would mean it would have 2 times 2 to the n minus 2 elements, which would be 2 to the n minus 1 elements. And is not cyclic, it turns out, because those two numbers, 2 and 2 to the n minus 2, would not be relatively prime. For example, if n here were 2, or 3, excuse me, if we were talking about U8, if n were 3, this would be z sub 2 external direct product with z sub 2. 2 is not relatively prime to 2. That actually is not cyclic. If n were 4, this would be u of 2 to the 16, 2 to the 4th, which is u of 16. If n is 4, this is going to be a z4 and a z2. That's also not cyclic. It's not going to be cyclic when n is greater than or equal to 3. On the other hand, u of p to the n when p is an odd prime is cyclic. For example, u3, 3 to the 1st. What would you get? Z sub 3 to the 1st minus 3 to the 0 power. 3 minus 1 is 2. Z2 is what it would be isomorphic to. Yeah, it's got 2 elements. U3 has got 2 elements, 1 and 2. U9, 3 squared, would be isomorphic to z sub 3 squared minus 3 to the 1st power. Z sub 9 minus 3 is z6. Yeah, U9 has 6 elements. What would they be? 1, 2, 4, 5, 7, and 8. Under multiplication mod 9. Talking about U9. It's got 6 elements. It's an abelian group with 6 elements. It turns out it's isomorphic to Z6, and it is cyclic. U of 27, 3 cubed. You'd have a 3 cubed down there minus 3 to the 2nd power. 27 minus 9 is 18. It'd be isomorphic to Z18. Combining these facts allows us to rewrite this isomorphism class in terms of cyclic groups. U5 is isomorphic to Z4, and U11 is isomorphic to Z10. I'm using this last fact in both of those cases. 5 is 5 to the 1st. 5 to the 1st minus 5 to the 0 is 5 minus 1 is 4. That's where the Z4 comes from. When I'm talking about U of 11, 11 is 11 to the 1st. 11 is prime. I get a Z sub 11 minus 1 is Z10. That's where the Z10 comes from. Do the same kind of thing with U75 here. U75. What's the prime factorization of 75? 75 is 25 times 3, or 3 times 5 squared. 3 and 5 squared are relatively prime to each other. So we can use the corollary to say this is isomorphic to the external direct product of U3 with U of 25, 5 squared. Yes, I could have written this as U of 25. And then once again, we go to this page, bottom of this page. I already said this, U3 is isomorphic to Z2. U25, we got a 5 squared there. That's going to be isomorphic to Z sub 5 squared minus 5, Z sub 20. This is isomorphic to Z2 external direct product with Z20. It looks like U55 and U75 are not isomorphic, but looks can be deceiving. These two things look different. They look like they're not isomorphic. Well, guess what? They actually are isomorphic. You just can't tell by looking at it. You need another theorem. You need another corollary in particular to see that they're isomorphic. You need this one right here. Let M be the product of a bunch of numbers. Zm is isomorphic to this external direct product. In other words, the external direct product is cyclic if and only if each pair of the ends is relatively prime. Each distinct pair is relatively prime. How could I apply that here? Notice that 10 is 2 times 5. 2 and 5 are relatively prime. Therefore, that Z10 could be thought of as the external direct product of Z2 and Z5. Because 2 and 5 are relatively prime, and 2 times 5 equals 10. And with this one, think about the factorization of 20. It's 4 times 5. 4 and 5 are relatively prime. I could write Z20 as the external direct product of Z4 and Z5. Now these are looking more alike, at least. They're still not quite exactly the same looking, right? Because the Z2 and the Z4 are switched around. Can I switch them? Do external direct product factors commute, so to speak? Yes, they do, actually. This is not labeled a theorem in the book, but it's worth knowing. I'm going to tell it to you right now, and it's something you should know for exams. The external direct product of two groups, say call them G and H, H is not necessarily a subgroup of G, is in fact isomorphic to the external direct product of H with G. Even if these are completely unrelated groups, and even if neither one is abelian. G and H don't have to be abelian here. They don't have to be related at all. This is still true. This is kind of a side note that's worth knowing. Why, you might wonder, why are these two things isomorphic? Well, we can come up with an isomorphism from one to the other, and I hope after a minute of thought, you'd realize the only possible thing you could think of as an isomorphism is this mapping. Phi takes the ordered pair G comma H to the ordered pair H comma G. That is a one-to-one onto operation preserving function. I won't take the time to check that. This is an isomorphism. It's pretty easy to check using what it means to be one-to-one onto an operation preserving and using what it means to multiply elements in external direct products as well. That's important too. So the upshot of that is that when you write something like this, you can switch these things around. You can say this is isomorphic to the external direct product of Z4 with Z2 with Z5. And therefore, it's isomorphic to this one. They are isomorphic, even though it seems like at first they're not.